Hey, what's up guys, my name is Cherno and welcome to an entirely new series, Ray Tracing. The series is ray tracing. This is both something that has been requested a lot and also something that I've always personally really wanted to do. So I'm happy that I finally have found the time to be able to sit down and do this. Now this video is going to be kind of like an introduction. We are going to actually write some code and make some pixels appear, and I'll introduce you to basically all the tools that we'll be using. However, we're not going to be getting into anything too deep today, which is actually a good thing because I'm going to give you all a bunch of resources, materials, prerequisites, everything so that you can kind of prepare and also work along with what we'll be doing without having to necessarily wait for me all the time to post new videos. For those of you who don't know, I'm developing a game engine called Hazel. That tends to take some time out of my day, so I'm going to try my best with this series to be consistent. Okay, so what exactly are we doing here? What are we going to be building? Building a ray tracer is an extremely vague statement because a ray tracer could be something that you could get done like in a couple days, in a weekend, knowing nothing about it, or it could be as large as something like RenderMan, which is used to render like all of the Pixar movies, Arnold, V-Ray, you know, all of those other renderers. Whilst I don't think we're going to quite achieve the latter, we are going to in fact broaden the scope beyond a basic ray tracer. So step one, obviously, is going to be something fairly simple. We're going to be starting by looking at the Ray Tracing in One Weekend book series by Peter Shirley. These are fantastic, and honestly, I think that if you are wanting to learn about ray tracing, you should definitely start there. What I'm going to be doing is essentially following this book series, implementing it here in video form, explaining everything myself, changing quite a few things, and making this more of like a real-time application rather than something that just writes pixels to a file. But the actual source content is going to be very similar to those books. We'll also be going further than that and actually implementing something that can render triangles. Triangles, of course, are very important because we need triangles to be able to render 3D meshes. The inspiration for this series came from me doing code review videos on my channel. You may have seen a few. It was extremely common for me to actually receive ray tracers that people had built. However, they were exceptionally slow. A little status update. I've been sitting here for about a minute. This is taking some serious time. Why is it so slow? It's rendering nothing. Well, I mean, they weren't all exceptionally slow, but I didn't see anything anywhere close to real-time interactive performance and frame rates, which is something that we're going to be exploring. A ray tracer running in real time? Yes, it's possible these days. In those code review videos, a lot of you liked the fact that I actually optimized the code and talked a lot about optimization. So that is one of the reasons why this series here exists. I'm going to be hopefully teaching you how you can optimize your code a little bit more using these ray tracers as kind of like the examples, the guinea pigs. C++ is of course the language we'll be using for this series. Sorry, Rust people. However, once we get all this up and running in a generally like good and optimized fashion in C++, we're going to be taking it to the next level and moving it to the GPU using Vulkan. That of course is going to be like a major kind of project in development, and it is much more realistic these days obviously to use the GPU for such tasks as ray tracing. This isn't going to be like an RTX kind of real-time-ish tutorial. It's actually going to be like a proper ray tracer, which will eventually become a path tracer that can render like arbitrary scenes, hopefully with photorealism, with the end goal of integrating this into the Hazel engine. So yeah, this is a pretty serious project. Anyway, hopefully you are all as excited as I am, but where do we begin? What do you need to know to be able to actually follow along with this series? So first and foremost, we will be using C++. If you don't know C++, I actually have a series on my channel where I teach C++. Hey, what's up guys? My name is Cherno and welcome to a brand new series. This series is going to teach you everything you need to know about C++. It's not the only way to learn C++, but it's not bad. We'll be using Windows and Visual Studio for this project. However, it's C++ and we're not going to be using any Windows API like explicit things, so it should be portable and run across all platforms. But if you're not using Windows, you're going to have to figure out how to get it to compile and build on your own for your platform. You don't need to be an expert in C++. I'm going to be explaining every line of code that I write, and besides, it's not really going to be about C++, of course. We're going to be talking about ray tracing, the algorithms that go into that, all of the math that you need, you know, that kind of stuff will be covered. So the programming language doesn't even really matter that much, but if you are familiar with programming in some respect, at least, that will be a huge help. The next thing that is extremely important, arguably more important than the first thing, is math. Turns out mathematics is pretty important. Now I'm going to try my best to explain like all the math stuff that we actually use and cover. However, I'm not going to explain like what a vector is and all those related operations like the dot and the cross product. I assume that you know all of that. If you do not, then you'll have to do some homework. Now, as far as where to learn math, I highly recommend that you take a look at Brilliant. They've also been amazing enough to sponsor this series. The kind of math that we'll actually be looking at, everything from algebra to actual geometry stuff, all of that is actually covered by Brilliant. And Brilliant being brilliant. I mean, I can't, like, you really need to actually try this out for yourself to see what I'm talking about. But the great thing about Brilliant is that unlike other like course platforms, it actually has extremely engaging and interactive courses. The best way to learn all of this mathematics and ray tracing stuff is by practice. You need to actually do the work yourself. Now, I don't know about you, and to be fair, everyone is different, but I'm an extremely visual learner. That means that if you're talking to me about vectors, for example, you need to show me a vector. I need to be able to visualize a vector in some form, because if I can see it, it just makes more sense to me. And that's what I love about Brilliant, the fact that they do have a lot of visual content, a lot of interactive content. They ask you questions, they quiz you, they keep you actively engaged so that you actually learn in the most efficient way possible. Now, if you already know all of the math that goes into ray tracing and you don't need to revise it, you might be interested in some of Brilliant's other courses. They have courses on computer science, physics, data structures, that kind of stuff. One of the best things about Brilliant is that you can actually get started for free right now. Just click my link in the description below. However, Brilliant have been nice enough to offer 20% off an annual membership for the first 200 subscribers who sign up using that link in the description below. Definitely sign up, explore some of their amazing courses for yourself. You really have to actually go through them to see what I'm talking about. And it's honestly a fantastic way to revise all of the math that you'll need for this series. Huge thank you to Brilliant for sponsoring this video. Once you've got all of the math stuff down, if I still haven't made my next video and you want more, then take a look at the Ray Tracing in One Weekend series. As I mentioned, we will be following this. Not like a one-to-one mapping, because I am going to introduce a lot of my own stuff and we are going to be writing the code in a slightly different, more performant style. However, they are fantastic books. They explain everything really, really well. They feature diagrams and all of that. I'll leave a link to this resource in the description below. I think that's a great place to start. There's also this website called Scratch a Pixel. Now, I've got my dark reader on, by the way. That's why everything's dark. Might not be like this on your computer. Don't worry, probably the same website. This will be in the description below as well. This is a little bit more advanced. However, it's more advanced in the way it teaches, but it's also more advanced in the actual like topics. So you can see that, for example, ray tracing a polygon mesh, this kind of stuff is a lot more akin to, you know, real world kind of ray tracing. Because as good as this Ray Tracing in One Weekend series is, it's not like necessarily the way that like a real ray tracing renderer actually works. And finally, if you've done all that and you still want more, then I recommend you pick up Physically Based Rendering from Theory to Implementation. This is an absolutely fantastic book. It's also a very thick book. It's very, very long. It's very complicated. However, this is one of my favorite books on computer graphics of all time. This has nothing to do with real-time rendering. I mean, this whole series that we're doing doesn't either. I did mention it would be in real time, but I mean, we're writing a ray tracer, so this isn't exactly going to be, you know, real-time performance with like maximum quality. It is still going to be interactive though. The scene that you actually see on the front cover was rendered using the renderer that you build in this book. I mean, it doesn't really show you how to build a renderer. However, all of the source code within this book actually comes together to form a renderer called PBRT, which is also available on the website of this book. I'm not sponsored by this book or anything, I just really like it. I'll leave an Amazon affiliate link in the description below, another great way to support the channel in this series. But yeah, in terms of like resources for ray tracing and rendering and stuff like that, that's definitely up there. That's pretty much all the material I can give you, I think. If you follow along with all of that stuff, you will be sweet. Believe me. In fact, you probably won't even need this series. But on the other hand, it's one thing to kind of read, you know, this stuff and another thing to put into practice. So hopefully this will still be helpful. So without further ado, let's begin. Let's set up our C++ project and actually get some pixels rendering. Now, a couple of weeks ago, I made a video where I talked about Walnut, an application development framework that I developed to make it easier to make applications, especially if they were kind of Vulkan related. As you can probably guess by now, that is what we'll be using as the base for this ray tracing series. So on my GitHub page, I have Walnut itself, which is this repository over here. You can take a look at that and, you know, see how it works and all of that. That is going to be the base library. Now, don't be too scared. This doesn't include absolutely everything that we might need. In fact, if you look at Walnut, it's just this. I mean, ignore the IMGUI stuff. It's just this. Like, the actual code that is already included here is really, really bare bones. That's the point of all of this. So don't worry. We're not going to be calling a function called trace rays and we're Gucci. Like, this is going to be, we are in fact going to be learning about ray tracing in this series. I've also got this repository called Walnut App Template. Now, this is basically like the starter pack for a Walnut application. You can see that Walnut itself is a submodule, and this has essentially an application that we can modify as a starting point to create Walnut applications. And in fact, because it's a GitHub template, you can actually press this use this template button. I can make a new repository called raytracing. And over here, I'm actually going to mark it as private for now. I'm going to make it public when I release the actual video that I'm making. I didn't really talk about this, but all of the code from like each episode of this series is going to be available for free on GitHub. Okay, that's pretty much it. Create repository from template. I've actually never done this before, so I hope this works. And there we go. We've literally, it's kind of like we've forked it. You can see it says generated from. However, like this is not, I guess, this isn't like a fork. It's just like a starting point, essentially, a template. So once we've done that, we're going to go to a directory on our computer, open up a command prompt, and you will of course need git installed for this. We're going to recursively clone that repository that we've just made. This shouldn't really take too long because Walnut isn't particularly big. Now, while this is actually happening, the only real other piece of software you'll need installed is Visual Studio 2022. Now, I highly recommend that you use 2022 if you can. That's what all the project files by default will generate into. And aside from that, you are also going to need to have the Vulkan SDK installed. I'll also leave a link to that in the description below. Okay, so this is what the root of the repository looks like. All you have to do is go into scripts and run setup.bat. Once that has run, you can see we have this walnut app.solution file. You should be able to open that and see that we've got basically our project. As a quick test, I'm just going to hit F5 to build and run it. And you can see we get our basic Walnut example. Now, all of that's great. However, I'm actually going to delete everything we've just done because I don't actually want it to be called Walnut app. I'm going to call it like ray tracing or something like that. If we open up the premake5.lua file in the root of the repository, this is where we can actually choose like a name for all of this. So I'm going to call this ray tracing. Maybe we need like another code name. Like what's another nut that we like a cashew or something? I don't know. If you guys have a suggestion for a name for this project, let me know in the comments below. For now, I'll just call it ray tracing. Really boring, but it makes sense, I guess. I'm going to basically just set the workspace to ray tracing, start project to ray tracing, and include ray tracing. Now, since I am including ray tracing, I'm going to have to rename this Walnut app directory to ray tracing, and that additionally also has a premake5.lua file where I also need to basically call it ray tracing. That is it. As far as I'm aware, that's all we have to do. Let's just delete these bin directories and all that stuff, and we'll rerun setup.bat. Now we have a ray tracing solution. This is still like the deleted Walnut app solution. We won't save that. We'll just open the ray tracing solution. Now it's called ray tracing. This is still called Walnut app. I can rename it to ray trace. Actually, we'll keep it as Walnut app because that's what it is. And then we'll just hit F5. You can see it now runs. Now let's talk about how we can customize this and actually render something. So step one is this is basically the normal kind of Walnut entry point. The only thing that we probably need to be concerned about at this point is maybe the title. I'm going to call this ray tracing. Now, whether or not we want like a file menu, maybe we don't want that menu bar, but for now I'll just leave it there. And we have two windows. We have this Dear I Am GUI demo window and this hello window. This is all dockable, and we can additionally drag these out. So it's just a really great starting point, honestly. However, we want to be able to actually render pixels. So what do we do? Now, what you're actually seeing here, like this entire window, this is all rendered using Vulkan. So if we want to render like a custom image, really all it's going to be is an actual Vulkan image whose pixels we can directly set. Instead of like loading a texture or an image file from your computer and then like displaying it here, we're going to be generating that data ourselves and then sending it to the GPU so that it can actually render it on our screen. Now, this does sound a little bit wasteful, and I mean, it is, right? Because what we're doing is we're generating the data. We're actually running all the algorithms on the CPU in C++, and then we're sending it to the GPU. Why not just run those algorithms on the GPU? That's what we will eventually get to, because that is so much faster than running it on the CPU. And we will see throughout the course of this series why exactly that is the case. So if we get out of this, what I'm going to do is show you guys how to actually load up an image, or rather create an image that we're going to be able to set the data of ourselves. So I'm just going to call this image. Now, it is a walnut image. However, what I'm going to do in this CPP file is just type in using namespace walnut, because everything's really going to be kind of from the walnut API here. Now, this begin window, I'm going to change it to be our settings, and this button's going to be a button called render. If we press this button, that's when I want to be able to actually render an image. So this is going to call a function called render. This video is going to be quite basic. We're not going to get too deep into like application architecture or anything. We will do that later, but not today. Now, when we hit render, if we do not have an image, so if the image is null, then we're going to create the image, and we're going to do that by just assigning it to scd make shared image, and then we have a bunch of parameters that we're going to take in with height, format, and data optionally. So the width and height, this brings us to what on earth is our width and height? Well, what we're going to do is we're going to make another window called viewport. So this is going to be, I'll get rid of that demo window. This is going to be our actual viewport. That's where we're going to see our rendered scene. Whatever size this is, which we don't really know, we're actually going to make a couple of variables here called viewport width and viewport height. We're going to ask ImGui if we do get content region available.x and .y here, we'll be able to actually get that width and height from ImGui. Now these are floats. I don't really want to store them as floats though. I'll store them as uint32ts. Width equals 0 by default, height equals 0. I'll call it viewport width and viewport height just so that it's extra clear. So these variables will now be how big this viewport kind of panel or window is in pixels. So this is obviously the size that we're going to use to actually make our image. Now, what happens if the panel resizes? If we actually resize this window, we need to recreate this image when we hit render, probably. I wouldn't ray trace like the whole scene if we resize it accidentally or whatever. We want to explicitly do that by hitting render. So that's where this comes in. So we not only recreate the image if it's null, we're also going to recreate it if viewport width does not equal the image width, so image.getWidth, or viewport height does not equal image get height. So if that is the case, we will resize it to the new kind of viewport width and height. The format, for now, we're just going to use image format RGBA. We will eventually move to like using 32-bit floats and all that stuff so that we can get some like high dynamic range. I almost feel the need to like just be like, guys, we're going to do this really exciting thing later. Like you'll see, I'm not going to reveal any more secrets from this series. You're just going to have to stick with it. Now, what about the actual buffer of pixel data? We need to also create that. So let's go ahead and create this buffer here called image data. I'll just have it assigned to null by default. We'll move it up here. And so what's going to happen is, first of all, because remember, this is not only happening if image is null, it also happens if we actually resize the viewport. So we want to, first of all, delete the old image data. If it's null, this will not do anything, and that's totally fine. And then we want to reallocate it. So we're going to just type in new uint32t, and it's going to be viewport width times viewport height. Now these are already uint32ts, they're not like uint8ts, right? So they're not just bytes, they're actual 32-bit integers. 32 bits, of course, is the size of the RGBA format. Each channel here gets 1 byte, so that gives us 4 bytes, 32 bits. So we don't need to like multiply this by 4 or whatever to get it to be like the actual size in bytes. These are already 32-bit integers. Now, let's go ahead and actually fill this image data buffer with some data, and then we're going to just send like this buffer to the GPU so that we can actually see it. So I'm just going to write a little for loop here. I equals 0, I is less than viewport width times height. So we're going through all of the pixels, and I'm going to set image data I equal to, maybe we'll just start off with like pink with magenta. So this is actually in like an ABGR format, meaning that these bytes over here are the alpha channel, this is the blue channel, this is the green channel, and this is the red channel. If you read it from like right to left, then you can see that it's the RGBA format. Once we've done that, we can set that data by calling image set data. And what this is going to do is actually upload this to the GPU. Okay, the last thing that we really have to do is actually display the image. So at the moment, we're not rendering anything, right? So we're going to call ImGui image, and then we're going to give it the descriptor set of the image. Maybe I'll change the Walnut API so it's a little bit more clear. And the size, this is a size in floats, is going to be image get width and float image get height. And that's pretty much it. Now, obviously, if image is null, which it will be for like the first few frames until we hit render, this is going to crash. So we're going to check to see if we actually have an image to display. And if we do, then we're going to render it as an ImGui image within that viewport window. So I don't know if I've done everything correctly, but let's just hit F5 and we'll see what we get. So first up, I want to actually kind of set up the layout. You'll only really have to do this once, and then it will be saved into the imgui.ini file. So if we just dock settings maybe to the right over here, and then we'll grab our viewport, dock it into the middle. This is kind of the look that I'm going for at the moment. And then if we hit render, hopefully we'll see this, which is basically this kind of just pink image. Now there is something that I want to kind of clean up a little bit, and that is this border that you kind of see here around the image. That's really, really easy to fix. All we have to do is before we actually begin the window, we just need to push a style var, and this is going to be imgui style var window padding, and we're going to set it to imvec2 0. And since we've pushed it, once the window ends, we're going to pop it. So pop style var. If we run that again and I hit render, you can see now it kind of fills that entire kind of space. Now, if I resize this and make it bigger, you can see that it doesn't stretch the image or anything because we're actually using the image's width and height when we render the imgui image. If we use the viewport width and height, it would actually stretch it. I don't really want that. So that's why the image isn't stretching. And if we hit render again, you can see it kind of renders using that new kind of area that we have. If I make it smaller, it'll also render presumably in that kind of smaller space. Now, how about something a little bit more exciting? Well, at the moment, the image is going to be the same all the time. However, let's add like a little bit of randomness, and we will need randomness when it comes to ray tracing as well. So we'll include the walnut random class over here. And then I'm just going to set this to be random uint. So this is going to give us like just a random unsigned integer. However, this is going to be fully random across like all the RGBA channels. I don't want the alpha channel to actually be random. I'd rather just have that be 1 so that we can actually see something all the time. So if I just go ahead and OR equals this image data by FF000000, that's going to just add in those kind of bytes. It's not going to add them, but it's going to set the kind of most significant bytes here to just be 255, right? Or most significant byte, which is the alpha channel. So once I've done that, let's hit F5. I mean, you don't have to do that. You'll still see stuff. It's just going to look a bit more solid with the alpha being 1. And you can see if I hit render, we get this image that's going to presumably be different every time. It's going to be super important to see how long these renders take as well. So what I'm going to do is actually just use a timer over here. You can include that by including walnut timer. And then at the end of this, I'm going to set the last render time to be timer.elapsed milliseconds. And we're going to make that float over here, set it to 0, and display it probably under, well, let's just do it maybe above the render button. imgui text, last render, 0.3f maybe ms for milliseconds, and last render time. So if we go ahead and run that, if I hit render, you should now see how long it actually takes. Now you might be freaked out. I mean, why is that taking 62 milliseconds? Most of it is actually going to be the random number generation, but also we are in a debug build, right? We're in debug. Debug's very slow. If we switch to release and run this, you'll see that it will be significantly faster. Okay, let's hit render, and you can see it's like 7 milliseconds or 5 milliseconds. Not very fast. I mean, if you think about like a typical frame budget of 60 FPS for a game, this is like a third, which is kind of worrying, but there's a lot of reasons for that, and we will get into them as the series goes on. Now, finally, 5 milliseconds is still kind of an interactive frame rate, so why don't we try rendering this every single frame? So what I'm going to do is just basically just add render to the onImgui render function. So this obviously gets called every frame, so that now this will also be called every frame. Let's see if that even works. You can see 5 milliseconds obviously per frame, and we have an actual kind of real-time beautiful renderer. Thank you guys for watching. Hope you enjoyed this very first episode of the ray tracing series. Next time, we're going to take a look at how to actually render like an object. We're going to be rendering a sphere, maybe a sky kind of background, something a little bit more interesting and tangible than just this kind of noise. In the meantime, I'll have a link to this ray tracing repository in the description below. Definitely download it, run it on your computer, make sure that it works, and that way you'll be able to follow along with the series really well. If you enjoyed this video and you're excited for this series, definitely hit the like button. Also leave your thoughts in the comment section below. Make sure you check out Brilliant using my link in the description below to brush up on your math. It's going to be very, very important for this series, and I will see you guys in the next episode. Goodbye.